Matan, the floor is yours.
Okay, תודה רבה. So I think I will give the talk in English, although Ofer told me I can do it in Hebrew, but if it's recorded, it might be better if it's in English. So I'm very happy to be here, even if it's not physically, and to show you my work on and my perspective on soil development and on and my work on Hillslope morphology and soil production in carbonate landscapes. And more specifically, I will focus on the influence of climate, vegetation, chemical weathering, and dust fluxes. Okay, so in my field, in geomorphology, we look at landscapes and how they evolve. And if you think about it, hill slopes, which I'm focusing on, is the most abundant landform on Earth. So on the continental Earth. So if you think about it, every inclined surface would be a hill slope. Hill slopes are often soil covered, and the soil covered hill slopes are usually have a distinct round and convex morphology. And many hill slopes are developed on carbonate landscapes, on limestone, chalkstone, סלעים גירניים. And you can see on the map that carbonate areas are very abundant on Earth. Okay, so the observation of convex soil covered hill slopes was made over 100 years ago, and it was addressed by this famous geologist called G.K. Gilbert, and he was the first to suggest a model to explain the stability of this landscape. Why is it so abundant? So what he explained that if you look at a hill slopes that is covered with soil, and if you imagine that soil is at some point upslope, soil is produced from the weathering of the rock beneath, then you have soil produced, but the soil is also transported downslope. And if you look down, if we go downslope, then we also have more soil produced, but we also get the soil that was transported from above. So to accommodate for this increase of soil flux and to preserve this this landscape, he explained that this is made by the increase of gradient, of slope. Okay, if a surface is steeper, you can imagine that soil will move faster. Okay, so this was his explanation, and many years later, in the 1960s, his model was formulated mathematically. So first, I'm showing you here. It's a soil mass conservation equation. Okay, it just states that every change in soil mass or thickness would be it would be the difference between soil production and net soil transport. For soil transport, we can state this mass transport law that just states some relation, in this case, linear relation between slope or surface gradient and flux. Okay, so for example, if the slope would be twice steeper, flux would be twice bigger. Okay, when I talk about soil transport, we refer to it as soil creep. Okay, it's a slow. It's not a mechanism. It's just it's a family of many processes that are slow, continuous, semi-continuous, and slope dependent. There are many mechanisms that can drive it, like rain splash, wetting and drying, and expansion of clays in the soil, small soil slips, freezing and thawing of ice, and also biological mechanisms like animals boring and pre-throw, and you can probably think of many more. Okay, so this is soil creep, and this is the transport law I'm using to describe it. And if I can take this transport law and place it in the mass conservation equation to get this equation to describe Hillslope evolution, the morphological evolution. And you might recognize it, it's just a diffusion equation. It describes many processes in nature, like heat diffusion, and processes in chemistry, and many more. And we know how to work with it and use it, and sometimes solve it. For example, one way to solve it, which I will show later, is for steady state. And this is also the case that G.K. Gilbert described. Okay, it's that a landscape that preserves its morphology, a soil-covered hillslope that keeps its convex round morphology. So we can solve this for and get a steady state solution. And you can see it's a parabola. It's a second order a polynomial, and you can just describe this landscape with a parabola. Okay, and you can graphically look at the solutions, and you can see that those parabolas, these convex hillslopes, get more round with this parameter, which is the ratio between soil production and this diffusivity or efficiency of soil transport. Okay, so it's actually the ratio between production and transport of the soil. For example, if soil production would increase, we increase the mass flux into the soil. So to preserve this morphology, we need steeper slopes. On the other hand, if we increase the soil transport efficiency, we don't need steep slopes, so the morphology would be less steep. Okay, and we can look at the first derivative of this solution, and we see that his slope increases with distance from the divide, and a second derivative, which is a constant number, which we call curvature. Okay, just a number that describes how curved the landscape is. So this ratio and relation between curvature and soil production and regolith transport coefficient is very strong, because it gives us a relation between a topographic parameter, which we can measure quite easily, and with two parameters that are very, very difficult, practically impossible to directly quantify, which is soil production and soil transport, which are processes that are actually too slow to actually measure on in geological timescales. So I just to show you how that this relation and this model is very widely used, I just dropped here a few recent papers from fancy papers in Nature and Science, and it's been used. It is being used very frequently, but practically all work that is being done is, except for very few studies, are made on silicate rock, not on carbonate rocks. And as I will show, it's important to notice the differences. Which brings me to my motivation for this work, for this project. So first is to better understand the evolution of carbonate hillslopes and their morphology, and more specifically to decipher and quantify the potential influence of chemical weathering and dust on hillslope morphology. Okay, so looking at the morphology of hillslopes in sites in Israel that you're probably very familiar with, it looks like the morphology is very convex, very classic. It's just parabolas everywhere. So apparently this classic model, this over 100 years old model, should work and we can start using it to study the evolution of hill slopes in this area. But knowing the special environment that in Israel and the East Mediterranean, we realize that there's a few things missing. So first is chemical weathering. We know that, for example, if we look at the soil and the rock underneath, in many hill slopes and places, the rock is, for example, it can be limestone or something that is almost pure calcite, and soil covering it can be very depleted of calcite. So there's obviously a difference between the rock and the soil. Okay, so if the model, it is an assumption in the classical model that all the rock that is weathered is converted to soil. So this assumption, it doesn't work when you have chemical weathering. Okay, so we add chemical weathering, this factor of chemical weathering, into our mass conservation equation. Another flux that we need to consider is dust. If the classical model assumes that all the soil is derived from rock weathering, once you have dust, it's an external source. So you have to consider it. And we add it also into the mass conservation. Dust in soils. So we have in Israel, there are some pioneering work in the subject by Dan Yelon and Yoel Dan in the 60s, and a few others, many others that follow them. And they showed that there's substantial input of dust in Mediterranean soils. We know that there's dust coming from far, from the Sahara and the Arabian Desert, and also there's local sources of dust in the northern Negev, in the lost soils. Okay, so what we did, we modified this mass conservation, and we get a modified expression for the curvature of the landscape that accounts for dust and chemical weathering, in addition to mechanical weathering and soil transport. And we can look at the graphical solution for the steady state solution. And so like soil production from rock, if we increase dust flux, we add mass. So to conserve the morphology, we need steeper slopes to accommodate for the increase in soil flux. And on the other hand, chemical weathering takes mass. So for a given amount of weathering, we need less steep hill slopes to transport the soil. So it will give, so chemical weathering, increase in chemical weathering will give us less convex morphology, less round, flatter. So we chose 7 study sites, which are marked in circles. Blue circles are non-durable, soft carbonate rocks like chalk and kirton, and orange symbols mark hard carbonate rocks, limestone, dolomite, סלעי גיר ודולומית קשים. And you can see that the study sites are scattered along a strong gradient in climate, or in rainfall, from the dry south on the almost arid conditions to Mount Meron in the north, where precipitation is almost 1,000 millimeters a year. But they're also scattered along a dust fall gradient, where the southern site in Gvot Goral near Be'er Sheva gets a lot of dust, and the north in the Meron mountain gets much less. This is to remind me that I will also show you results from a work we did on cinder cones on the Telima volcanim in Ramat HaGolan, and I will talk about later. Okay, so much of my work in my PhD was to think of ways to quantify all these parameters in this modified equation. So I will go very briefly on the methods. So to quantify the topography or the curvature of the actual curvature of the landscape, we used high resolution topographic data. We quantified denudation rates or weathering rates using cosmogenic nuclides, specifically chlorine 36, to quantify soil transport and transport efficiency coefficient, this K sub S. We use the numerical modeling, which I will show, and some remote sensing. And we also did some work with short-lived isotopes in the soil, which I will only show if I have some time at the end. To get dust flux and chemical weathering, we used measurements of concentrations of immobile elements. And some other methods we did some work with scanning electron microscope, grain size distribution analysis, and mineralogy. Okay, so high resolution topography is we just had for each of the study sites we had laser scans of the landscape. It penetrates. It's called LiDAR. It penetrates vegetation. Now this is my main field of work, working with topographic data and analyzing it, but I will not go much into details here. I can really give a few talks just on this subject. So if there's any interest to anyone, please feel free to contact me. Sampling, we sampled in each site, we sampled the bedrock and a profile of the soil covering it. So we sampled it for analysis. In the field, we also sieved. We built this big sieve, mesanenet, napa, and we sieved it to fine and coarse material. Okay, immobile elements. So by measuring two immobile elements, when I say immobile elements, I mean a chemical element that is present in the soil, and it's chemically very stable. So if there's any chemical processes, any washing of the soil, it will probably stay in the soil and just get enriched. Okay, so if we have two, for example, let's say I called it immobile elements X and Y on these vertical and horizontal axis. So if we see the immobile elements in the rock and in the dust, we expect that the soil will be somewhere along a mixing line between them, unless there is chemical weathering which enriches the immobile elements. Okay, so the amount of enrichment or the amount of chemical weathering we can quantify just from how much this line, this sample is enriched, and the place of our sample along this line will show us how much of the soil is dust and how much is rock-derived materials. Okay, so but we don't do it graphically. We have equations to calculate it for the fraction of dust and the fraction of chemical weathering or enrichment of the soil. Cosmogenic nuclides. It's a method, a chemical method that practically revolutionized the field of geomorphology. Today is almost the only way to give us rates on long-term processes in geology and geomorphology. And to be very, very, very brief, cosmogenic nuclides are unstable isotopes, usually unstable, could be stable, that are not they're not formed, you don't find them naturally. They're only produced from the heating of solar cosmic rays on surface elements. So for example, if we have calcium in our calcite rock, it will produce chlorine 36. And if we know the rate of production and we have ways to estimate it, we can say something about the rate of erosion or the time of exposure of the surface. I hope I was clear about it. Okay, so to quantify the efficiency of soil transport, we went to the Golan Heights, and we went specifically to the cinder cones, the Telima volcani in Ramat Golan, and we looked at the hill slopes there. So first, we chose 5 cinder cones, which are scattered along a strong rainfall gradient in the Golan Heights. And the reason we did that is in the Golan Heights, first we eliminate the influence of dust because there's very little dust in the Golan Heights, but there's also and the little that there is invariant in the Golan Heights, so we can ignore it. And also we expect not much chemical weathering because it's silicate and it's fresh. It's 100,000 years old minerals, so we expect that there wasn't much chemical weathering. Okay, so it allows just to isolate the influence, the environmental influence just on soil transport. Okay, so as I showed you before, one way to solve the diffusion equation is to look in equilibrium, in steady state condition. But here we take another approach and we just solve the equation numerically. So it's an approximation of the solution. We use a finite difference method. And to do so, to solve numerically, we need a boundary or initial and final conditions and time of for the time steps of the model run. Okay, so what I mean, we need to know what was the initial morphology of the cinder cones. So there are studies about morphology of fresh cinder cones, so we know it should be something similar to a cone, a conus volcani, and we know what should be the gradient of the hill slope. But we also can measure it in some of the cinder cones where we have excavations into the hill slope. We can measure the inclination of the buried tuff layers, and so we can estimate the initial morphology. The final morphology, we just measure the morphology today in the field with very accurate surveying or with flying drones. And time. We know the time of the evolution because these cinder cones are dated radiometrically. And we specifically chose cinder cones that are about the same age, over 100,000 years. Okay, so we are left with only one missing parameter, which is the one that we are looking for, which is the efficiency of soil transport, which is, it's kind of it's a black box. We don't really know what influences soil transport efficiency, but as I show you, we can say something about it. Okay, so we just run the model for a range of values for this parameter, for this diffusivity coefficient, and we find for the best fit solution. Okay, on the left, you can see if a value too high would give us an overshoot. A value too low, we not develop the morphology enough. And the big on the center here, you see a good solution of the numerical model. So I'm jumping right into first results. So these are the results of the numerical model. And what you can see here, that the efficiency on the of soil transport on the vertical axis, it decreases with rainfall on the horizontal axis. Okay, so it means that as in the Golan Heights, as the rainfall increases, soil transport is inhibited, which is it was a surprising result for us, because I expected that we have more water, more rainfall, things will move faster, but it's the other way. So we thought about we asked ourselves, how can that be? And the way we explain it is with vegetation. The Golan Heights, it's not arid, but it's still water limited. So every increase in rainfall, in mean annual rainfall, will give us denser and longer periods of vegetation cover, which we believe stabilizes the soil. Okay, and on this plot you can see a vegetation index from remote sensing of many cinder cones in the Golan Heights with our 5 in yellow triangles, and you can see that it increases with mean annual rainfall. Okay, so this is what we think. I'll skip this. Just to say that this work was published in 2017 in ESPL with much more details. Okay, regolith composition. So, as I said, we sampled soil in each of the study sites, and we sieved it to coarse and fine material. So, first thing I want to show you that we found that coarse material, which is bigger than 2 millimeters, is between 25 and 50% of the soil mass. And this is important for us as geomorphologists, because for us, soil is everything that moves. And so for us, this is also soil. I know any analysis is made on just on the fine fraction of sub 2 millimeters, but we need to account for all the soil if we want to consider the evolution of the landscape. And also, it gives us indication now things that are bigger than 2 millimeters has to come from rock weathering. They cannot come from dust. It's too heavy to be transported by dust. So it gives us an indication of mechanical weathering of the rock. Okay, results, chemical weathering from immobile elements. So we found that this is a result just on the fine fraction. And we see that chemical weathering increases dramatically with rainfall, which is not surprising. If you get more rain, more dissolution of the calcite, so you get more chemical weathering. And we did that using two sets of immobile elements, titanium and yttrium, and cesium and lanthanum, and results are convincing. Same for dust. We see that as we go from the dry south to the wet north sides, and actually further from the northern Negev, we get less and less dust in the soil. So in the south, we get one is 100% soil. So near Gvaot Goral, the fine fraction of the soil is practically almost only dust. And if we go north, all the way to the Meron, in the Meron, it's very little dust and perhaps even no dust within the uncertainty of our method. And also with these different sets of immobile elements, and results are still convincing. And if you're still not convinced, these are results. The images are from insoluble residue of the soil from 3 sites, from the Meron in the north to the Den Mountains to Bet Guvrin in the Shfela, and you can see that in the insoluble residue of the soil. So dissolves all the calcite, the grain size gets bigger as we go south. And we also see it in using a device that measures grain size distribution. And it's nice to also look in the Shvela, in the bed Govrin regolith. So we see very large quartz grains in the soil. But if we look at the insoluble residue of the rock, of the chalk rock that is underneath, we find very fine. It's all micro fossils, and it's really very beautiful things, but it's very obvious that the fine fraction, much of the fine fraction in bedrock soil is not derived from the rock, probably dust. Okay, so this is a graphical summary of the results on soil composition. So we see that in all the sites, coarse fraction is, as I said, between 25 and 50%. There's obviously sufficient mechanical weathering going on, which is, in spite of some studies that say the contrary, there's only mechanical weathering. And we can see that in the south, in green, the fine fraction is mostly dust derived. And as we go north, there's more and more in the light gray, which is rock derived fine fraction of the soil. Okay, and this was published in Geomorphology in 2019, if there's anyone interested. Again, these results are from the cosmogenic nuclides. These are denudation rates. Okay, so it's measurements of the rate of surface lowering of the in our study sites. And we can see that denudation rates increases with rainfall. And because we have our results from the immobile element, we can differentiate how much of the denudation is mechanical and how much is chemical. And we see that on the left, on soft carbonates, on the kertonin, the weathering is mostly mechanical, but it's also very high. So the chalkstone weathers faster and mostly in mechanical processes, and hard carbonates weather slower, but it's about half of it is mechanical processes, half of it is physical processes that weather the rock. Okay, so I showed you how we quantify results from all the fluxes that we have, and we only left with how the topography, the actual curvature of the landscape. And as I said, we used topographic analysis from high resolution topography. And what we found is that as we go from the south, the dry south, to the convexity of the landscape decreases. Okay, so if here in the south, if you can imagine that if you walk from the hilltop, and you start walking down slope, you very quickly becomes very steep. And as we go north, here, for example, in Matan Ben Asher, it's much smoother landscape. But as we go further north, there's some increase again. And so if we looked at our modified expression for the curvature, it works nice with our results, because if we go from south to north, we know that in the beginning we have a strong increase in chemical weathering. Yeah, there's a minus before chemical weathering, so it will as expected, it will decrease curvature. Also, we know we have a strong decrease in dust fall. So also, if it's in the equation, it's in the mechane. So if we have increase in a decrease in dust flux will decrease, we expect to decrease curvature. And the denudation rates should act the other way. If we have more higher denudation rates, it should increase, but it's apparently it's the chemical weathering in dust flux that are more dominant in the southern sites. And in the northern sites, the north sites, we have this sudden increase. It makes sense because the chemical weathering is high, but it doesn't change much. It's just very stable, high and stable. It doesn't vary much. And same for dust flux, it's low and doesn't vary much in the north. But the inundation rates are increased very rapidly. And this is why maybe we see this strong increase. But this is calculated curvature because we have all the fluxes. We can see what is the actual expected curvature from the measured fluxes we have. So these are added, I just added down now in the yellow circles, in the blank circles. So we can see that in the north, our measurements and our model actually fits really well with the measurements, okay, which is very nice because it's completely independent measurements with a almost conceptual model, but apparently it works really nicely in the northern sides. But in the southern sides, there's a misfit. And it looks like the convexity of Hillslope is higher than we would have expected to see in the morphology, which is also very interesting because, to remind you, Hillslopes evolve in hundreds of thousands and millions of years. And the fluxes we measure today, some of them like dust, we measure actual fluxes today that are represented in the soil today. And maybe it teaches us something about past environments and changes in environment we had before. So we can have a long discussion about, we made a long discussion about it, but for example, one reason we think is maybe dust fluxes were actually even higher in the past, and the morphology preserves these past conditions. So all the discussion and results are in a recent paper from 2021 in GSA Bulletin, and you can read more about it or contact me. Okay, so to summarize this part, so we saw that dust in the soil and regolith is comprises between, I said 15%, but it could be zero at some samples, to almost 100% of the fine fraction of the soil. So it varies. And we see that it correlates nicely with current dust deposition rates. Chemical weathering, we see that it increases with rainfall, which makes sense to us. And we see that chemical weathering is higher on hard carbonates, which also we think it has to do with the permeability of the rock and the ability of washing the soil into the rock. Soil production. So I don't think I didn't show it, but we actually have numbers, measurements or estimation of long-term soil production rates, and the range between 20 and 200 grams per square meter per year. So I don't know if there's anyone who, considering the environmental regeneration of soils, maybe these numbers can be very useful. We saw that soil production increases with rainfall, again, in our study sites, and is the result from both mechanical and chemical processes, in addition to dust, of course. Soil transport. So we showed that at least in the environment that we studied, And the climate we studied, soil transport is controlled by rainfall through the influence of vegetation cover that we think is stabilizing the soil, which of course have many implications in conserving, in soil conservation. And about the morphology, so of the hill slopes, so we show that at least in our study sites in the Eastern Mediterranean, it's classically convex and it has a characteristic curvature value. So each site are pretty much all the hilltops are very similar in their convexity, but different between sites. And we believe that they record and they are influenced by chemical weathering and dust flux, in addition to other environmental parameters. And we want to highlight the possibility that form process relationships in other rocks, like silicate rocks, should also consider these fluxes and should be modified, because chemical weathering happens not just on, it's very strong in carbonate rocks, but it happens on every rock. And dust, of course, just not just in the Eastern Mediterranean, dust can be in many places in proximity of deserts. Yeah, I will leave you with these. And I want to thank you. And I'll leave you these pictures of my current study site here in France. And I'll be happy to take any questions.
Matan.
Sure.
The floor is open to questions. Who would like to go first? If nobody volunteers, I have a question. It regards the last slide before the conclusion.
Yes.
So you've shown that the model doesn't fit the southern sites very well, and you suggested that this could be because of much higher dust flux in the past. And there are studies of those estimated dust fluxes. What happens if you plug the numbers into the model? Will it make sense?
We have estimation of dust fluxes today.
Or let me ask it differently. What should the dust flux in the past have been for the model to fit? And do those fluxes make any sense?
It's a good question. I didn't try it, although I think the works that you're talking about is by one of my advisors on COVID. We didn't try it, but this model that in results I showed you with the convexity are based on the assumption that all the fluxes are steady. So once they are changed, it doesn't really matter. All we can say that they were higher. Because once.
But how high should they have been for the model to fit the observations?
Yes.
And yes, I was referring to On's studies. I think he collaborated with Yehuda Enzel, but there are also other estimations from Ben Gurion University by Chaim Zohar. And
yes,
I'm not familiar with the current literature on that.
Yes, I'm trying to find this. Yes. Okay, so we can see here. Sorry, I'm having. So you can see that, for example, here on the southernmost side, the curvature is 10 times higher than we should have been expected. So because it's a linear ratio between in this equation, so dust fluxes, if we leave all the rest the same, so dust fluxes should be almost 10 times higher. But again, you need to differentiate between dust input, dust deposition, and dust accumulation. Because the studies today that show how much dust is settling, but we don't know how much stays in the soil, because some of it goes through chemical weathering and some are recycled and redeposited. But so the input of dust should be about 10 times higher.
But is that corresponding with what we see with, for instance, the formation of the less soil in the northern Negev?
That's what I'm trying to say, that we cannot really, we need to be very careful when we compare past, like the numbers we get from the lost deposits are accumulation rates. It's how much actually accumulated.
Which is what is important also for this case, yeah?
Yes, but we don't know how much, how it is today, because we only know how much is settling in a dust trap. So I cannot answer you. I can do the calculation. So a very rough estimation will be 10 times higher than today.
Okay.
But it's complex because there are a few assumptions for the steady state that are, and how much of this dust remains in the soil that is difficult to answer.
אפשר לשאול?
בבקשה, פנחס.
שמחה.
אני אשאל בעברית, כי זה נראה לי, אין בעיה. א', ברור שבדרום המודל צריך לחזות הצטברות ולא שטף, ברור שבדרום השטף הרבה יותר גבוה, לא פי 10, אולי אפילו פי יותר מזה. אבל אנחנו רואים במפנים צפוניים, בצפון הנגב, בנגב עצמו אין הצטברות בכלל, אבל בצפון הנגב, בגבעות גורל ובית גוברין, מפנים צפוניים מאוד שונים מדרומיים, וזה בגלל הצמחייה, ושם אפשר להעריך את קצב הצטברות האבק והקרקע. אבל אתה אמרת בעצמך שהתהליכים של יצירת קרקע הם בני עשרות אלפי ומאות אלפי שנים, אבל אתה מדבר על תהליכים שקורים היום. אתה מדבר על קצב יצירת קרקע של 20 עד 200 גרם למטר מרובע לשנה, אני הבנתי נכון?
כן.
זה הרי, זה מספר שהוא בלתי אפשרי לחלוטין, הן מבחינת קצב הצטברות האבק, שזה מילימטרים לאלף שנה, לפי הערכות של יעלון ושל אלי גנור, וקצב הבליה הכימית, בייחוד על סלעים גירניים, אני לא מדבר על הסתברות של גיר רך ברנזינות רכות, אבל גיר רך על קרטונים רכים, אבל כשאתה מדבר על קרקע, אז בייחוד על סלעים קשים, זה פשוט בלתי אפשרי, כולל בקרקעות רנזינה, אין כאלה קצבים, זה פשוט בלתי אפשרי, גם מבחינת קצב הבליה, גם מבחינת קצב ההצטברות. עכשיו, טילי געש בגולן, אתה מדבר על תהליכים של היום, באקלים של היום, כאשר הטילים האלה נוצרו 100,000 שנה אחורה, לא קדימה, באקלימים שונים לחלוטין מהאקלים של היום, אז אינני יודע, עכשיו הפרופיל שהראית שם, הוא פרופיל אולי של הצטברות, ולא בהכרח פרופיל של גלישות, או של שקיעה, זה בזמן שהאפר הוולקני, זה מה שיש שם. שקע, הוא לא בהכרח שקע במורפולוגיה, ולפעמים הוא שקע תחת מים, אז זה בכלל תהליכים, אז הכל טוב ויפה, אבל אם אנחנו חוזרים למספר של 20 עד 200, זה נראה לי לא סביר.
אפשר להעיר פה משהו?
כן.
אנחנו מצאנו, לא בשנים האחרונות, אבל בנגיד בין לפני 20 עד 10 שנים, בסביבות...
מי הדובר?
אלי, שמי אלי. בין 100 ל-120 גרם למטר מרובע באזור של עבדת ובאזור של אופקים. כלומר, המספרים שהוא אומר הם מספרים מאוד ריאליים.
בוודיות או ב...
לא בוודיות. או בוודיות, במפנים צפוניים ודרומיים, באזור עבדת ובאזור של אופקים.
אוקיי, בסדר. אני דבק במה שאמרתי קודם לכן. קצבים כאלה היו הופכים את הקרקעות שלנו לקרקעות של מישורי לס של סין של 400 מטר או יותר עובי, בעוד שהלס הכי עבה אצלנו, וגם הוא פלובייטילי בחלקו, הוא לס של 12 מטר. אז אני אינני יודע מאיפה אתם לוקחים את המספרים שלכם. אבל זה סותר כל עבודה קודמת שנעשתה, לפחות נכון שזה היה על ידי אנשים שלא השתמשו בשיטות, אלא המודרניות שמשתמשים בהם היום, אלא יותר בטביעת עין וידיעת השטח, אבל זה עדיין, אם אני לוקח את העבודות של גנור על הצטברות אבק, הם דיברו על מילימטר ל1,000 שנים, איך אנחנו מגיעים ל-200 גרם למטר מרובע? זה לא יכול להיות פשוט. מבחינה כמותית, אני יודע במקום מסוים, באתר ספציפי. אבל בבקשה, זה נחמד מאוד אם זה כך.
אז אני... טוב, ציינת המון דברים שיש לי אל כולם הרבה דברים להתייחס. אני לא אתווכח על המספרים, אבל כי בהחלט אפשר להתווכח עליהם, אני לא...
המודל שלך מוביל למספרים, אז אם המספרים אינם נכונים, המודל אינו נכון.
אוקיי, אז מודל הוא אף פעם לא נכון, הוא תמיד, הוא צריך לזכור שהוא כלי להבין תהליכים. וזה משהו שימש אותנו. המטרה שלנו לא הייתה להשיג מספרים, אגב, אני אף פעם לא מציג את המספרים, פשוט כי זה מחלקה לקרקע וסביבה, אז היה לי חשוב להראות את המספרים. בהחלט אפשר, אבל אפשר גם לדבר על זה, אבל נראה לי, אני רוצה לפתוח פה את הוויכוח. עכשיו, לגבי הערה שלך על המודל ברמת הגולן, אז אתה צודק, אנחנו מסתכלים על 100,000 שנה שהאקלים מאוד השתנה, אנחנו כן מאמינים שהגרדיאנט האקלימי שאנחנו רואים, שבכמות המשקעים, נשמר. זאת אומרת, גם יבש יותר, גשום יותר, גשום פחות, הגרדיאנט נשמר כי הוא מושפע מהטופוגרפיה של רמת הגולן. וזה כנראה אפקט אורוגרפי. אז זה התירוץ שלנו, למה זה בסדר, וזה נכון. זאת אומרת, המספר שאנחנו מקבלים הוא לא מייצג להיום, לאקלים של היום, אלא הוא ממוצע על כל תקופת התפתחות המדרונות שם. סתם לדוגמה, אם היה לי תל בגילאים של כל 10,000 שנה, אז הייתי יכול להגיד לך מה קבוע כל 10,000 שנה. שהייתי מאוד רוצה לעשות את זה, אבל לצערי אין לנו את זה. אני יכול להגיד לך שאם אנחנו עושים את זה לתלים, יש שם תלים של כמעט 1,000,000 שנה, אנחנו מקבלים ערכים הרבה יותר נמוכים. זה רק מראה שבאמת על תקופת זמן אחרת, ואקלים אחר אנחנו מוצאים משהו אחר, וערכים אחרים, כי זה ממוצע התקופה עם תנאים מאוד שונים, אז אתה מאוד צודק. אני מאוד שמח ששניכם ציינתם את העניין של המפנים, כי השקופיות בסוף שדילגתי עליהם, זה בעצם דברים שעשיתי, הסתכלתי על המפנים. אז גם ברמת הגולן, בכל תל שאפשר היה, הסתכלנו על מפנים שונים, ואנחנו רואים את ההבדלים בין המפנים ביעילות זחילת הקרקע, שזה, שוב, זה מחזק את העניין של הקשר לצמחייה. שוב, יש לנו גם ידיעות ממש לצמחייה מפגישה מרחוק להבדלים. זהו, אז אני גם מנצל את ההזדמנות להגיד שחזרנו לאחד לתלים האלה לאחרונה, לפרויקט, אין ממש תוצאות כאילו בעשייה, אבל בגלל שיש לנו, כבר מכירים אותם טוב וקצת מבינים את התהליך שקורה שם, אז אנחנו הסתכלנו שם על הפחמן האורגני בקרקעות, בתל, גם פרופילים, גם לאורך המדרון, וגם השתמשנו אני מתפרץ פה, למרות שלא שאלתם, אולי זה יעניין מישהו, איזוטופים קצרי חיים, צסיום ועופרת, צסיום 137, ואנחנו מכירים מניסויים גרעיניים, ושגם יכולים לשמש אותנו לתת איזושהי הערכה על תנועה של קרקע, אנחנו מחפשים, בעצם זה עבודה על הקשר בין התפתחות המדרון, תנועת הקרקע, סחיפת קרקע לפחמן שבה. כי יש פידבקים, כמו שראיתי, יש פידבקים בין צמחייה לפחמן בקרקע, לזחילת הקרקע. זהו. מקווה אני יודע שלא עניתי על הכל, מקווה שעל חלק.
מישהו רוצה לשאול עוד משהו או לחדד לגבי שאלה קודמת?
דרך אגב, אולי הערה על בית גוברין, שברי הקרקע שאתה מוצא שם, השברים בקרקע שאתה מוצא שאינם מן הסלע, זה מהנארי, שברי נארי פשוט.
הנארי?
הציפוי... כן, כן.
כן, הנארי זה... לנו זה אסון, הוא מאוד מסבך את הסיפור. אני הופתעתי חיכיתי שמישהו יעלה את הנארי, אתה צודק, זה מסבך. אני יכול להגיד לך, שלמשל איזוטופים קוסמוגנים בכלל לא עובדים שם בנארי. זה בלגן מאוד מעניין, זאת אומרת בפני עצמו זה נושא שאני חושב שרק מהעבודה הזאת, דווקא יש לנו הרבה תוצאות מעניינות על הנארי, אבל כן.
אם אתה לוקח דרך אגב בקרקעות, אמרת מה שגדול מ2 מילימטר הוא לא קרקע, הוא כן קרקע. אתה לוקח את השיטה האמריקאית, את הקלסיפיקציה האמריקאית, יש להם למה שמעל 2 מילימטר, יש להם שמות פרגמנטל, יש להם כל מיני שמות אחרים, שמציינים את הפרקציות הגדולות מ2 מילימטר, עד נדמה לי 7.5 סנטימטר. אז זה כן קרקע, לפחות לפי האמריקאים.
אני מסכים. תואר ראשון שעשיתי קורס בקרקע, ההגדרה שאני קיבלתי היא הלכלוך של הסלע.
טוב, זה גם מורפולוגים וגיאולוגים.
כן, בדיוק.
נחמד, עבודה מעניינת, ושילוב של שיטות פשוט מאוד מאוד מעניין, שאנחנו כוותיקים לא מכירים אותם בכלל.
אז אני אשמח לפרט אם זה מעניין מישהו, ואני בהחלט לוקח את ההערה שלך על הקצבים. אני מודה זה לא שאלות שעניינו אותי, אבל זה מעניין, גם לשאלה של עופר להשוות אותם, להסתכל על הקצבים, בעצם מה צריכים להיות הקצבים של האבק, וגם כמה זה ריאלי, זה מעניין, פותח את הראש. תודה.
אני אוסיף, יש איזה מאמר מלפני כמה שנים שמתאר מנגנון מעניין של ספיחת חלקיקי אבק אל תוך הקרקע על ידי קרומי קרקע ביולוגיים. זה מאמר של חבר'ה מיוגוסלביה, אני לא זוכר מאחת המדינות שם, נדמה לי מסרביה, שהציע את זה כמנגנון מרכזי בהיווצרות של לס. זאת אומרת, לא רק צמחייה, אלא גם משהו באמצע בין הצמחייה לקרקע. בכל אופן, מעניין מאוד, תודה רבה מתן.
בכיף, ותודה רבה לכם על ההזדמנות.
דק לי יפתח.
פה יש רק פייר ופרנסואה, אבל אני אחפש יפתח.
להתראות.
ביי.
ביי ביי.
תודה.